Okay, so thank you for this wide audience for the first lecture. So these classes will be about for 24 hours until the first week of March. The classes is about an introduction to enumerative, algebraic, and bijective combinatorics. So the first lecture will be an introduction to the course, introduction to the introduction. I will just give you an idea what means enumerative, algebraic, and bijective combinatorics. So first, what we mean by enumerative combinatorics. I will give in this lecture some example. A very simple example, how many permutations on n elements? The number of permutations, here is a permutation. It's a one-to-one correspondence from a finite set with 10 elements here to a finite set with 10 elements. And the number of such permutation is n factorial. 1, can multiply 2, can multiply 3, can multiply n. Or you can see also permutation as a word. A word is n letters. The letters are 1, 2, 3, 4, 5 until n. And you put a certain order on the list of letters, 3, 1, 6, 10, 2, 5, 8, 4, 9, 7. So the choice of the first element, there is n different ways to choose the first element, then n minus 1 to choose the second, n minus 3, etc. So you get very easily this very simple enumerative problem, number of permutation. In the class, there will be many, many times permutation appearing in this lecture. A much more deeper example with Young tableau. What is a Young tableau? So first, you define a partition of the integer n. Here n equals 12. And a partition of 12 is just a sequence of numbers, strictly positive, such that the sum is going to be 12. The order of this number does not involve, so you can put this number in decreasing order, 5, 3, 2, 2. So this is the partition of the integer n. It's a very classical combinatorial object, going back to Euler in the 18th century. And you can visualize this partition by what is called the Ferrer diagram. So you put the cell like this, you have a hook here and a decreasing stair like this. And the first number 5, you put 5 as 5 cells on the first row. Then you put 3 cells, then 2, then 2. So the total number of cells integer 5, 3, 2, 2. So we call this lambda, also lambda. The shape, this will be the shape of the Young tableau. And physicists call this a Young diagram. Combinatorists call this Ferrer diagram. And well, it's two different worlds, but they will mixed in these classes, physics and combinatorics and algebra will mixed. So this will be the shape, lambda, of the Young tableau. You give Young tableau first, you give a shape, you give a partition of n. And a Young tableau is a filling of the cell of the diagram by number 1, 2, 3, 4, 5, 6, 7 until 10 n equals 12. So you put the number in the cell, satisfying the 3 following conditions. First, each number appears once and only once. So you have the 1, the 2, the 3, the 4, the 5, 6, 7, 8, 9, 10, 11, 12. So each number, 1 to 12, appears one and only once in the diagram. Second condition, the number go increasing in each row when you read from left to right. So this go increasing, 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 increasing. And third condition, the number go increasing also in column when you go from bottom to top. This is called a Young tableau of shape lambda. Lambda is a partition. So combinatorial problem. What is the number of Young tableau with a given shape? You fix the shape. How many ways you can fill up your diagram satisfying the condition increasing in row and column? I will call this number F index lambda. So this is a typical combinatorial problem, enumeration of such Young tableau. Sometimes it is called standard Young tableau because there is some other kind of Young tableau where you can repeat the letter, which are called semi-standard. But what is the number of such objects? And there is a very, very beautiful formula. It's a deep formula. It's not easy to prove. The problem is simple. You can explain this to your kid in elementary school. You can explain the formula to kids, but the proof is really difficult. This is the magic of enumerative combinatorics. So the Hook-Lens formula is the following. First, I have to define the hook of a cell. Take any cell in the diagram, and the hook of a cell, to take this cell, for example, the hook is simply all the cells which are above this cell, or the cells which are on the right, and the cell in itself. So for each cell of the diagram, I have a hook corresponding to the cell. The hook length is a number of cells of the hook. So here the hook length is 5 because there is 1, 2, 3, 4, 5 cells corresponding to this hook length. Now for each cell, so you can put in green numbers. I put a number in each cell, which is the hook length. For example, here I put a 8 because 1, 2, 3, 4, 5, 6, 7, 8 cells. I put 2 here because 1, 2, 4, 1, 2, 3, 4. So for each cell, you associate the hook length. All these green numbers. And now the magic formula. The magic formula is that the number of Young tableau with the shape lambda is exactly n factorial divided by the product of all the hook lengths. So this is a non-trivial deep formula. First you have to show that the product of all these green numbers is going to divide n factorial, and the ratio will be exactly the number of Young tableau of given shape lambda. For example, for this hook length, for this shape, n factorial divided by the product of hook lengths give you 4,455 possible Young tableau. So it's a magic formula. There is many different proofs. Let's go back to McMahon, and then there is with determinant, and then this hook length formula was framed in the 50s, and then many other proofs, what we call bijective combinatorics, but it's really deep. So I will give another example of enumeration with the so-called binary tree. And this enumeration, then you are going to use one of the fundamental tools in enumerative combinatorics, the use of generating function, which is just a formal power series, the formal power generating function. So this will be chapter 1, around generating function we will call ordinary. You will see why. So here is a binary tree. This is a fundamental object in computer science. Every recursive program involves binary tree. So a binary tree is a triple. You have the root of the binary tree, which is here, the root. And then there is a left subtree and a right subtree, which are also binary tree. So here is the left subtree, this one, and here the right subtree. And to stop this recursive definition, we are used in computer science to give recursive definition. In mathematics, maybe it's not very common to define binary tree by itself, involving L and R are again binary tree. And then to stop it, the binary tree can be reduced to a single vertex, which is an external vertex. So the vertex in black, where there is a left and right binary tree, are called internal vertex. And the vertex here which stop the recursive definition, this one are called external vertex. And if there is n internal vertex, here you have 1, 2, 3, you have 7 internal vertex. There is n plus 1, there is 8 external vertex. So another combinatorial problem is to find the Cn, the number of binary tree. What is the number of binary tree? Having n internal vertices, equivalently having n plus 1 external vertices. So you get a sequence of numbers, C1, C2. So C1 equal 1, C2 equal 2. The next one is 5. There is 5 binary tree with 3 internal vertices. The next one is 14. So 1, 2, 5, 14, 42. This is a very classical sequence of numbers. So this is classical old combinatorics. You work with recurrence relation. To define a binary tree, it's just you define the left subtree, the right subtree. They are totally independent. So you have a certain choice. If there is I vertices, you have Ci possible choice. On the right, you have Cj possible choice. And the total will be I plus j plus 1. So you have to define a binary tree on n plus 1 vertices. If you delete the root, then you have a choice of left binary tree, a choice of the right binary tree. So you get this recurrence relation starting at C0 equal 1. So this is a classical, I should say all combinatorics, recurrence relation. And then you have to solve this recurrence relation. Solving it, you get this very nice formula. So else you have a different possible proof, or else you check that this number satisfies this recurrence relation. So you have this very nice formula. The number of binary tree with n internal vertices is a binomial coefficient 2n chosen divided by n plus 1. So C is for Catalan. These numbers are very classical. It's Catalan numbers. It go back to, Catalan was the 19th century. In fact, it's go back to Euler again. Euler defined this. We will see in the class how he did not define with binary tree, he defined this with triangulation. But this is another example, and the use of generating function. Now, in the class, I will not do recurrence relation. I will go straight with the modern proof, what Flageolet called symbolic calculus. So, what is a binary tree? The definition of a binary tree is else is reduced to a point, a single external vertex, or else it's a triple with a root, a left binary tree, and a right binary tree. So we will see, we will define formally some equation at the level of combinatorial object. Binary tree is defined by this equation. And then we'll show that we can project this equation on the field of calculus of generating function. So we'll do this, we will do formally, but I will just give you an idea. But with this will be real proof. We just change binary tree by y. So binary tree become y. I am going to do calculus. Y equal, this is 1, plus, it's this or this, and the root is going to come for t, and again, y and y, two binary tree. So this will be, you will understand in chapter 1, this will be rigorous proof. So from binary tree, I project the definition onto the level of calculus. So I get an algebraic equation. And this equation, what is y? Y is precisely the generating function for Catalan number. So we say a generating function is the formal power series, 1, t, and t2, t3. The coefficient of t power n is cn. So I will explain, I will recall you what is a formal power series. This is the introduction to analytic calculus. So this is a polynomial, if you stop at n, and the formal power series plus point. It's, I will explain this, the algebra of formal power series. And in general, if you have any sequence of numbers, or any sequence of anything in a ring K, then you get the generating function for this sequence. And then, so from this, so we get the algebraic equation. From the definition of tree, you project on the level of formal power series, and you get this algebraic equation. And then if you solve this, find the coefficient of t power n in y, then you get immediately, for a few calculus, you get the Catalan numbers. So this is a modern way to do combinatorics. No more recurrence relation. In fact, the recurrence relation of the beginning is equivalent to this quadratic equation. But now we go straight away from the level of combinatorial object to the level of calculus and generating function. Now I give an example for the chapter 2. Chapter 2 will work with what we call exponential generating function. Here it was ordinary generating function. Ordinary because I just put the number Cn in t power n. But sometimes we use another kind of generating function, exponential generating function, which is good for what we call exponential combinatorial structure. Like permutation will be in this kind of object. So very often, you see, in the reverse in combinatorics, you have a sequence of numbers, and then you want to have an interpretation of these numbers in terms of combinatorial object. So here is a famous sequence of numbers. 1, 2, the next one. No, it's 16. 1, 2, 16, 272. So this is a very famous. Everybody recognizes this sequence. Well, this is at elementary school in trigonometry. Yes, trigonometry. This is a coefficient. If you write in exponential generating function, so the coefficient of I put odd numbers, 3, 5, 7, and you see you have t power n divided by n factorial, and this function is the expansion of tangent t. So it's sinus divided by cosinus. So if you expand in Taylor function, in generating function tangent t, you get exactly, in exponential generating function, you get some integer, 1, 2, 16, 272, and question, what does it mean? This number can be interpreted in terms of some combinatorial object. So you need some imagination. The reverse problem, if I give you a binary tree, okay, count binary tree, okay, this is Catalan, you have the formula. But the reverse, I give you the numbers or the formula, what they are going to count. They count something. And the answer was given by Désiré André in about, at the end of the 19th century. He defined what is called alternating permutation. So what means an alternating permutation? So here is a permutation on 9 elements. So it's the number 1, 2, 3, 4, 9 are in this order. So it's a word in this number from 1 to 9. This is a permutation and definition. a permutation is called alternating if and only if you have this condition. When you read from left to right, the second element is less than the first one. So we call this a descent. Now the next one is bigger than the, so a rise, this is a rise. When this element is bigger than this one, it is a rise. When this element is smaller, this is a descent. So for any permutation, you have what we call the up-down sequence, the sequence of rises, descent, and alternating means that it go down, up, down, up, down, up, down, up. You never had a double rises or a double descent. So this is a special class of permutation, alternating permutation, going descent, rise, descent, rise, descent, rise, descent, rise. And Désiré-André shows that the number of alternating permutation on 2n plus 1 element, on an odd number of elements, the number of such is exactly the coefficient of tangent t in the Taylor expansion. So, for example, there is 272 alternating permutation on 7 elements. So this kind of magic. How did he? We don't know how he. Maybe he was defining this, playing with this, and he realized that this was the coefficient of tangent t. In fact, in the old time of Désiré-André, he has a recurrence relation. This is a recurrence relation. This is the number of alternating permutation on 2n plus 1 element. It's going to be a little analog of Catalan number, but there is a binomial coefficient here with a product of 2. So you have to show that alternating permutation on 2n plus 1 element can be defined by a pair of 2 smaller alternating permutations of a choice of a binomial coefficient. So again, this was in the old time of combinatorics. And to check that this recurrence relation is exactly the same as the coefficient of tangent t. In fact, this recurrence relation of Désiré-André, it's equivalent to say that tangent t, this generating function, can be defined by this differential equation. In fact, this differential equation is equivalent to this recurrence relation. Now, modern combinatorics, we don't need any recurrence relation. We start from this. We don't know anything about alternating permutation. We want to have interpretation of the coefficient of tangent t, of these numbers which are integer. We start from this differential equation. And the standard modern technique, we will explain this in chapter 2. We will automatically get the alternating permutation. So how it works, I give you a rough idea. Maybe I go fast, but don't worry. In the class, I will explain everything slowly. I have plenty of time to do this combinatorial class. I have even several years. This is the first introduction to combinatorics. There will be some other classes to more advanced. So instead of starting, I prefer in combinatorics of the differential equation, you can also start from this integral equation that the y tangent t is t plus integral from 0 to t of y2 dt. So this is at the level, again, of analytic calculus. Now we are going to rise at the level of combinatorial object. Starting from this formal power theory, we go to combinatorial object. It is very easy. You replace small y by capital Y. You replace t by capital T. So now this is a combinatorial object. I am looking for a combinatorial object which is else is reduced to a point which will be weighted capital T, or else it will be this. So now this means integral of the pair of two combinatorial objects. So this will be well defined. The integral of something. And the solution in terms of combinatorial object is the following. We will apply the general theory in chapter 2. So what I am looking for is something, it's a combinatorial structure on a set of endpoints. Take endpoints 1, 2, 3, 4, 5, 6, 7, n. And what I am looking for is else reduce a single point, or else it will be something I take my point 1, 2, 3, 4, 5, etc. n. They are totally ordered. There is some label 1, 2, 3, 4, 5, n. I put the minimum here. I put aside minimum here, and on what remain, I make a partition in 2 blocks, and on each block, I put a structure of the type Y. Right. Y will be a certain commental structure on a set of n elements, and this structure is equal to else reduced to a single point, or else I put apart the minimum element of the set. On what remain, I make a partition in 2 different blocks, and on each block, I put again a structure of the type Y. So if I do this recursively, I get this. Here, the set of elements is 1, 2 until 9. You put here the minimum element, 1, and on each block, one block is 3, one block is reduced to 2, 4, 5, is this one, and on this block, I put the same structure, taking apart the minimum element. On each block, I put, again, each time you put the minimum element on here, and each time you repeat the same recursive construction, and you get this kind of things. So what is this? It is binary tree. It is some binary tree, the same as before, counted by Catalan numbers, but now there is some label on the binary tree. The label are 1, 2, 3, 4, 5, 6, 7, 8. And the label go increasing when you start from the root and going down in the binary tree. So for each vertex, the left son, the root of the left subtree, the right son, the root of the right subtree is bigger than this label. So we call this increasing binary tree. It's binary tree labeled by 1, 2, 3, 4, 5, n, and the number go increasing when you go down in the binary tree from the root to any other vertex. And I claim that this such binary tree, increasing binary tree, give an interpretation of the coefficient of tangent t on an odd number of vertices. Now, how to get the alternating permutation of Désiré-André? Now you have a local bijection. This was a general principle. Now I apply a local bijection to put this as an alternating permutation. And we will see this is one of the fundamental bijection in the class, bijective class of combinatorics. I am going to take a projection of this tree like this. You project, you are going to smash the tree, and I'm reducing the length, you see, of the. All this will be defined rigorously in the class, but you see, to get a permutation. I just repeat the projection. If you are a computer scientist, this is looking the binary tree in order or symmetric order of the binary tree. Every computer scientist knows this, but this is visual way to define the bijection. So you have the projection of the binary tree. You have to reduce the length, and then this is an alternating permutation. And this is a bijection between increasing binary tree and alternating permutation. So you see, this philosophy of this class is we have some general principle to work with differential equation at the level of combinatorial object. I will define what means the derivative on object, the sum, the product, which project at the level of the ordinary or exponential generating function. So this is general principle. And then we have a local bijection between increasing tree and permutation. Yes?
What about the number of alternating permutations of even?
Even. This is 1 divided by cosine. There is another interpretation for even. It's the inverse of cosine, the function cosine. And again, there is another system of differential equation. And this will be increasing binary tree where there is one vertex is missing at the left. So this is an analog. So we are going in the idea of bijective combinatorics, where we try to avoid calculus and to replace this calculus by some construction or algorithm. So this is another example of a planar map. What is a planar map? You have a a planar graph. You have a graph with some vertex, some edges. Maybe there is multiple edges. Maybe there is loop. And the planar map is a way to embed the graph inside the plane. In fact, it's not the plane, it's a Riemann sphere. I embed this in a Riemann sphere, so you can move this on the sphere. And we are going to count such objects. So this is not very good to count. What is very good to count is rooted planar maps. You need to start somewhere to do some algorithm or bijection. So rooted planar maps mean that one of the edges is distinguished with a certain arrow on it. So you go from this to this. So this is much simpler to enumerate rooted planar maps. And Tutt, in the 60s, he gave a whole sequence of papers to enumerate such planar maps. He was trying to solve the four-color conjecture at that time by enumerating planar maps and four-color possible planar maps. And he gave us this very beautiful formula that the number of rooted planar maps with m edges is exactly this. So it's 2 times 3 power m divided by m plus 2 multiplied by the Catalan number. So this is an amazing formula because you have the Catalan number here. So this means the number of trees. Catalan number is the number of trees. Now multiply by 3 power m means you are going to put 3 colors on each vertex. Or maybe, in fact, the bijective proof, you can choose this. You put a little edge here, 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 or here. So it's 3 different ways to add a certain little edge. Divided by m plus 2. So the number of external vertex is m plus 1. But if you add one more here, this will give you m plus 2. So maybe in the class I will give you the bijection. It's a deep bijection. It's not easy. But behind each planar maps, there is a trees behind. So you have to, bijective quadratic is to try to explain this formula. Tutt proves this by recurrence relation, classical. It is difficult to show this formula using, he used the iterating function, recurrence relation, all this. Kernel method, so is this sort of sophisticated technique. But if you can prove it by using directly Catalan number, which are binary tree, 3-color binary tree divided by m plus 2, so it's kind of cyclically regarding cyclically the binary tree. So this has been done. And there is an explanation. There is a proof, a bijective proof of this formula using trees and some sophisticated construction. So each planar map, there is a tree behind the maps, and then from the tree you can add many edges to get a bijection with planar maps. So all this was a lot of activity. Corey-Vauquelin in the 70s, they gave a proof, but not a proof of the formula with Catalan number, a proof of there is a system of algebraic equation for the iterating function. So, but they gave the first bijective proof. Then it was improved by Arques, and then Schaeffer gave a direct proof of the formula here, a direct proof of this formula. So this was very nice because in his proof, he can prove there is many other formula, and in a single bijection, he can prove 4 or 5 different formula. And then this bijective proof was improved by physicists. And why they were very interested in this? It's because it was used in the so-called field in theoretical physics called quantum gravity. They have to find they have to study random maps. You take random maps, mean any maps with images, you take it by random, and then they have to define the geodesic on the map, etc. And the bijection give you many more information than the formula, which are useful for the physics. So they were very excited. This was one of the first, they need really the bijective proof. The calculus proof is not enough to do what they want to do in this field of physics called quantum gravity, the unification of quantum mechanics and and general relativity. So we are very far from combinatorics, but you see combinatorics now interplay very strongly with some part of the new physics. So what we mean by this was the bijective proof of a number of planar maps. What do we mean by bijective proof? An example with RSK for Robinson, Schoenstedt, Knuth. Let's go back to the Young tableau. So take n equal 4. This is all the possible partition of n equal 4, all the possible shape. This is 1 plus 1 plus 1. This is 2 plus 1 plus 1, 3 plus 1, or 2 plus 2, and 4. So this is all the possible partition. And this is a possible number of Young tableau for each shape. So there is one Young tableau, 1, 2, 3, 4. Here there is 3 Young tableau, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Else you make the list, or else you apply the Hook-Length formula. So total number of Young tableau is with 4 elements is 10. Now if you take the sum of the square of this number, 1, 9, 9, 4, 1, take the sum, you get 24. 24 is the number of permutations on 4 elements. So this is a magic identity that n factorial, the number of permutations, is exactly the sum over all partition of n, all possible shape of Young tableau on n elements, and you sum the square of the number of Young tableau with a given shape.
So there's no simple formula just for sigma f lambda?
For f lambda? Sigma is, yes, this is a number. We will see, this will be a consequence of the bijective of this, that there is a simple formula to relate the neighbor involution on n elements, which is easy to count. But the most important fact is this identity. So bijective proof of this means that there must be a bijection between permutation. And here, what is this? It's a pair of 2 Young tableaux of the same shape. So there must be a bijection. A bijection between permutation, this is n factorial. You make the sum all possible shape. So this is f lambda for a given shape. And if you take a pair PQ, this is f lambda to the square. This identity, I can give a proof of this identity if I get a bijection between permutation and a pair PQ of 2 Young tableaux of the same shape. And this is the famous Robinson-Schoenstedt correspondence, which I will explain in chapter 4. This is one of the magic of the key, one of the diamonds of combinatorics, this bijection. You can try to find a bijection by yourself before I give you the bijection. And I am sure that if you find a bijection, it will be equivalent to the Robinson-Schoenstedt. If you find another one, which is really different, this will be a big event in combinatorics, but all the bijections, there is different way to define the bijection. There is 4 or 5 different ways, and all the ways are equivalent. So it's a kind of canonical bijection. Why? It's all possible way to define bijection. Go back to the same same bijection. It's because there is some deep things behind. This is like an iceberg you see on the sea. This bijection, this is the visible part of the iceberg. Every kid, I do this with my grandchildren. I explain this in elementary school. You can define the bijection different ways. They play with this. There is a very beautiful manipulation. You don't need to know anything. Just to compare two numbers and agree to go north, south, east, west, to be able to make difference between the color. But behind there is some beautiful and deep mathematics. Behind this bijection, this is a repression theory of finite groups. So so this is called algebraic combinatorics. It's a typical example of algebraic combinatorics. It's a relation between algebra and combinatorics. Algebraic combinatorics, sometimes you start with some classical algebra and you are going to interpret this in a combinatorial way. So we have representation theory of groups, and the combinatorial interpretation will be Young-Tableau, Robinson-Schoenstatt correspondence. Or sometimes the reverse way, by using theorem for algebra, from geometric algebra, then algebraic geometry, I mean, then you can prove some theorem in combinatorics. So this is a very exciting field because you have an interplay between algebra or algebraic geometry and combinatorics, which are very, very exciting. So this is a typical example of algebraic combinatorics. So representation theory of groups, if you don't know anything about it, just give you an idea that you have groups and you want to have to represent the group as a group of transformation or a group of n by n invertible matrices. So you see, so you have a homomorphism from a group to a set of invertible matrices, and every representation of a group can be defined. There is a decomposition, what they call irreducible representation. Analog where any numbers can be written as a product of prime numbers. So this is some analogy. Every representation is defined from a decomposition with irreducible representation. And then for the symmetry group, the irreducible representation are in bijection with the partition lambda of n, the group of permutation on n elements. And the dimension of the irreducible representation, I mean the dimension is the size of the matrix. When you are going to send the group into a set of n by n matrices, the dimension of the irreducible representation is exactly the number of standard Young-Tableau of shape lambda. So you give the shape, you give the Hook-Length formula, and the number of Young-Tableau is going to be exactly the dimension of the matrix with n row and column. So it's a big matrix. The other example was 4,455. So this is big matrix. And this is the classical stuff in group theory. And then we know that in every finite group, the order of the group, the number of elements of the group is exactly the sum over all irreducible representation of the square of the degree of the representation. Degree means the size of the matrix. So in the case of symmetry group, you get this formula as a special case. And the Robinson-Schoenstatt correspondence gives you a bijective proof of this formula for symmetric, for the symmetry group, which is one of the main example symmetry group. It's related to symmetric functions, Schur functions. There are many other things, and we have a good representative of all this theory here with Amri, where he can write his book, read his book in the Cambridge Unity Press about representation theory of groups. So to make a summary of this philosophy of bijective combinatorics, of bijective proof of identity, you have a certain identity, and bijective proof is to replace equal by a one-to-one correspondence by some bijection, some correspondence. And the interest of this is you have a better understanding of the formula. For the planar maps, it's very essential that you have better understanding, which give a very beautiful application in physics. So I like to call this a bijective paradigm, to see all identity like a bijection. And so bijective, so we can, you have some calculus, and you replace each part of the calculus by some picture, some combinatorial object. So you are drawing calculus. I am going to show an example. Calculus becomes, each part of the calculus becomes some picture, some combinatorial object, and so you replace calculus by some visual object. Or conversely, you are computing with drawing. I mean, drawing is a combinatorial object, and in the previous example with tangent t, I have defined the integral of a combinatorial object. So I am computing on the set, I am defining the product integral of combinatorial object. So I am computing symbolically with a picture, with figures. So all this will be rigorous in chapter 1 and chapter 2 about. So I give you an example of this interplay between calculus and visual way to see the calculus, to replace some part by picture, by combinatorial object, and then to do the calculus on the set of figures of objects. So I will give you a beautiful example with what we'll call a Meller identity on orthogonal polynomial. So we are with the Hermite polynomial. It's a very simple class of orthogonal polynomial. And I will give you an idea, again, an idea of this philosophy of proving the identity with calculus on the picture or drawing calculus. So here is the identity. So this is the Hermite polynomial. There is two Hermite, no, there should be an n here. There is two Hermite polynomial. And this is an exponential generating function of the product of two Hermite. This is n here. And this is the right-hand side is this. So when I began in combinatorics 40 years ago or 50 years ago, I remember there was a meeting, and this was a whole talk, 1 hour talk, to prove this was a whole paper. Now this is a simple exercise. In 5 minutes, I will prove this in 30 seconds. In 1 minute, I will prove this with 10 slides. And this will be, at the end of the class, you will understand this is really rigorous proof. By associating to each of these parts, I am going to associate some picture, some combinatorial object. So now this is an easy exercise in any combinatorial class. So first, the Hermite polynomial. Here is Hermite. Hermite polynomial is a polynomial in one variable depending of the index n. It can be defined in many different ways. It's orthogonal polynomial. But one way to define it is by defining with the exponential generating function. So Hermite polynomial is the exponential of this, of xt minus t2 over 2. As a formal, it's a formal power series in t, written in exponential form with a weight, with a certain extra variable x. Now I am going to translate this into pictures. So x is going to be this. 1 point with a loop, a blue loops. So this will be, t will count, it's a variable, will count the number of points. There will be many points. If there is t2, there will be 2 points. And x, there will be a weight x on these blue loops. A weight is just, I will consider x as a formal variable. And now minus t2 over 2 will be this. So t to the square because there is 2 elements. This is written t2 over 2 factorial. It's written in exponential form. And minus 1, there will be a minus 1 weight on this. So now I have to take the exponential of this. Exponential of this plus this. This with the weight minus 1. This with the weight x. So exponential means you take many of this. So many. This is taking the exponential. This is taking the exponential of xt. Exponential of xt minus t2 over 2 is exactly doing this. This is standard combinatorial technique. So what I get, here you have a certain configuration on n points, n equal 10. You take 10 points, and on these 10 points, you have some block. You have a partition in blue block, reduced to a single point, or some blocks reduced to 2 points. So we have certain partition of your endpoints into block of 1 point or 2 points. And on each block of 1 point, you have a weight x. And block of 2 points like this, you have a weight minus 1. In fact, this is an involution. This is the permutation, involution. All the cycles are length 1 or 2. And to give answer to our rule that number of standard Young tableau, if you take P equal Q, then this is exactly involution because the magic of the Robinson-Schonstedt correspondence, if you take a permutation, you get a pair PQ, and if you reverse Q and P, you get the inverse permutation. So if the permutation is an involution, you have P equal Q. So standard Young tableau P are in variation with PP, which are involution. Involution are exactly this. Involution are only permutation with cycle of length 1 or 2. So Hermite polynomial, in fact, are defined by you take all possible involution on a set of n elements. So all possible permutation with cycle of length 1 or length 2. This is a cycle notation of a permutation. And then you put a weight, x for each single point, -1 for each pair of length 2, and the total weight of the configuration is the product of all the weight. So you will have x power 5 multiplied by -1 power 3. So the Hermite polynomial can be defined as the following. You take all possible involution, all possible configuration on n elements, all possible partition in blue and red blocks, and then for this configuration you have a weight, x power number of blue point, -1 power the number of red cycle. You sum over all possible involution and you get exactly the Hermite polynomial. So this was the definition by exponential generating function is equivalent to this definition in a completely commutative way. So this is a classical commutative interpretation of Hermite polynomial. Now let's go to prove this formula. So first, the left-hand side, here you have an Hermite polynomial in red. So this is the interpretation of the Hermite polynomial. Fixed point, block with 1 point, block with 2 points. Everybody is red now because of the red Hermite. Now the second Hermite polynomial. You have again another configuration in blue. First Hermite, second Hermite, and you make a superposition of the two configurations. The blue and the red give you this kind of picture. Now it's you see some there is some connected component like a chain like this with 2 loops at the end, or there is some cycle inside. If you superpose 2 involution in blue and red involution, you get this configuration. So this is the left-hand side. Now the right-hand side. Else I can work directly with this, or maybe if you allow me to put this inside. So small calculus, I put this inside, and then I get this exponential of all this. So this is the sum of this term, plus this term, minus this term, minus this term. So there is 4 terms. I decompose in the bracket 4 different terms, and each term is associated to a certain picture, certain drawing. So this term is going to be associated to this. So just believe me, I go back from calculus to picture. This term is associated to this, red, red. So say you have an alternating chain in blue and red, and blue, blue, red, red, and this one, blue and red. So this was the 3 terms, and there is another term. This one, logarithm of this will be cycle, non-oriented cycle. Just believe me, it's standard technique in combinatorics to translate this into this. You will see in the class, this is easy techniques to translate calculus to picture. Now I have to take the sum of all this and take the exponential. Exponential means many. You put many, so you put this kind of things. So this is the right-hand side. There is cycle, there is chain, 3 kind of chain, alternating chain, and 1 kind of cycle. This was the left-hand side. So they are the same. And that gives you the proof of the identity. So this is typical example of drawing calculus or calculating with drawing. I take some part of the identity. This will be the cycle. This will be this chain, 3 kind of chain. This will be cycle, and taking many of this, and this is the left-hand side, superposing 2 Hermite configuration. So this gives you an idea of the philosophy of this bijective combinatorics. So I will explain all this in a visual way, formal way, and you will understand, and you will see, oh, this is easy. This identity, now I understand. I understand better the identity than doing it just by recurrence relation or calculus. So we have many identities, many bijection, and what I call bijective tool. So this kind of like a star in the sky, and you have each blue point is a formula. So there is a jungle. Now there is so many formulas, so many identities. Even not only identities in combinatorics, like what is a number of planar maps, okay. But you see there was this bijection. Instead of proving combinatorial identities, now you can prove much more general identities if you put some weight. Weight can be with variable x, y, alpha, beta, gamma, like the Hermite polynomial. There was a weight x. But there is something much more, we can go much further by putting, for example, the Laguerre polynomial depends on the parameter alpha. There's a Askey-Wilson polynomial with 5 parameters which are strongly related to some model in physics. There's a Q, alpha, beta, gamma, delta. So what we do is we have on both sides the same number of objects, but we put some weight, alpha, beta, gamma. It's formal variable, and as soon as the bijection preserves the weight, then we have some identities with the weight. And then the weight alpha, beta can be a real number, a complex number. So we get some identity much more general than just enumeration formula. So this combinatorics now is in training many different fields in mathematics, especially classical analysis with orthogonal polynomial, conjugate fractions. There are many parts of pure and classical mathematics which can be done in a combinatorial way, even if we don't see at all any combinatorial formula, any enumeration, because there is this weight preserving bijection. So I suppose I have many identities, a jungle of identities, and we try to put some classification, some order. This is a starting point. To have some enumeration formula, or more general formula with some weight, this is a starting point. It's not the ending point. Of course, sometimes it's very difficult to find how many ways to do this and this, to find a formula for the enumerative problem, but this is a starting point now to go further, to try to do some order in the jungle, to do some theory, some model. And then there is each of the identity can be explained by some bijection. Some bijection can explain 3 or 4 different identities. So now there is a jungle of bijection of correspondence, and we need to put some order in this, all this bijection. So this class I will do in this year and next year is to try to all the possible bijection to do what are the basic bijection. So there is so many bijections, so I will explain in the class the main bijection, which for me, a basic bijection is a bijection which can be used many times in different combinatorial problems, and also some people to find new bijection, but this new bijection, it's just a combination of this, and this. So new bijection, it's just a sequence of basic bijection. So I try to put some order in all these bijective tools, and to put some order, maybe there is a more general level, what I call bijective tools. A bijective tool is something, a general lemma, a principle, from which you can deduce many different formulas, or many different bijection. So I call this basic tool, bijective tool, or basic lemma. And I give you an example of this. It's trying to put some order in all this beautiful sky. So I give you an example. The Hook-Length formula and the tiling of the Aztec diagram. So we have seen the Hook-Length formula. There is a direct proof for the Hook-Length. Now a totally different problem. The Aztec, very beautiful problem. The tiling of the Aztec diagram. So here is the Hook-Length formula on Young tableau, you remember, n factorial divided by the Hook-Length. And here is the Aztec problem. So here is the Aztec diagram. Why it's called Aztec? Because you see it's like a pyramid, Aztec pyramid in South Mexico. And there is a lake, there is a reflection of the pyramid in the water. So this is the Aztec diagram. And the tiling of the Aztec diagram, you have you are covering this diagram with some dimers. It's two consecutive cells. It can be vertical or horizontal. And the tiling, they not overlap, and they cover the whole diagram. So this is a possible tiling. And now what is the number cometal problem? What is the number of way of covering the Aztec diagram with the tiles, like this? And there is a very beautiful formula. Very, very beautiful formula. Again, a deep formula. The number of tiling of the Aztec diagram with dimers is exactly 2 power 1 plus 2 plus 3 plus n. Very beautiful formula. The power of 2. Or if you prefer, it's 2 power nn plus 1 divided by 2. So try to give a proof of this. So the total number of tiling is 2 power something. It's very beautiful. If you take a rectangle instead of Aztec diagram with dimers, vertical, horizontal, there is also a formula for the number of tiling, but it's totally different. It's with a P of cosinus, tinus. There is a Castellin formula which was introduced for the Ising model in physics. It's a terrible formula. It's completely different. Not nice as this formula is 2 power something. This was proved by 92 by these 4 people. Now I claim that there is a proof of this formula using a certain bijective tool, a certain lemma. This lemma says that under certain conditions, if you want to count configuration of non-crossing paths, like this, the starting point are fixed, ending point are fixed. There is some path, sequence of elementary step. So under certain conditions, the number of such non-intersecting paths is exactly given by a determinant. So this is an example of what I call a basic tool in combinatorics. And there is hundreds of formula in combinatorics where some determinant appear, and all these formula can be proved using this basic lemma. And for this formula, for the Aztec diagram, this can be put in bijection with a configuration of non-crossing paths, and this is given by a determinant. And the same for this formula. In fact, it's not exactly, it's a semi-standard Young tableau. This is the limit of the formula for semi-standard Young tableau. This also can be put in bijection with non-crossing confusion of paths. So both problems, Hook-Length formula and Aztec diagram, are under the same roof of given this by a determinant as soon as you have a bijection between this and configuration of some non-crossing paths and some determinant. So you use the same basic lemma, the same basic tool to prove two completely different problems. So another example of basic tool is what is not yet very well known, but it's what I call heaps of pieces. The idea of putting some heaps of pieces, like heaps of diamonds on a chessboard. And so there is a formal definition of this. You can put weight, you can put heaps of anything onto anything. And there is 3 basic lemma. And from these 3 basic lemma, you can prove many completely different problems. You can prove involved in algebra, in physics, in analysis, on orthogonal polynomial, or in statistical mechanics with percolation, with directed animals. So there is many, from the three basic lemma, then you get many, many things, or the rotation of Lie theory also, Coxeter group. Many things can be done using, so this is what I call the, under the same roof, heaps of pieces, you can have many different cometal formula, many different proof of identities, and so this begin to put some order in the jungle of identities. And so combinatorics is a fantastic field because it's organizing, it's an old field and a new field where a lot of things has to be done. And so this will be the starting, so this Thursday, the course will be, so first, chapter 1 will be about ordinary generating function, like the Catalan numbers, the number of binary trees. So this will be, so I will prove, I will give the, recall what is the formal power theory, and I will show you operation on to make rigorous the proof I gave you with binary tree, how to replace binary tree by the generating function and get the algebraic equation. Then chapter 2 will be about exponential generating function and exponential structure, like the Meller formula for Herbit polynomial. So you will get rigorous proof of the Meller formula for Herbit polynomial for this. Then we will go back to the ordinary generating function, so bijection for the Catalan garden. Many bijections are in fact related to, in the world of Catalan, there is trees, paths, non-crossing partitions. So there are many different objects are counted by Catalan numbers. So I try to put some order in all the bijection and to give you only maybe 10 basic bijection, which can be useful for many different problems in combinatorics. There is a book by Stanley on Catalan numbers, and he says there's about more than 70 or 80 different interpretations of Catalan numbers. So there is 80 to the square possible bijection, but I will just retain the basic, the main bijection, because I know I have used this, or other people have used this in many different problems. Then we will do the same for the world of n factorial. So many objects are counted by n factorial, like the pair of Young tableau. So I will explain the Robinson-Schoenstatt correspondence. I will explain some other tableau, some other objects which are related to the so-called PASEP model in physics, the partially asymmetric exclusion model. So there is some objects which interpret the stationary probability in physics, which are again counted by n factorial. So there is many objects counted by n factorial. And then chapter 5 will be about this relating, tiling, determinant, non-crossing paths, Schur functions. There are many things related to non-crossing paths and determinant. And so this would be about 24 hours. And if I have time, I don't know. Usually I go too fast, so I will try to go slowly, all these 5 chapters. If I have time about the combinatorial theory of a differential equation, you get an idea with a tangent T, with a differential equation which are interpreted by alternating permutation. So this is my main website, is this. And there is a secondary website where you can get the slides. So I put already the slide of this chapter, of this introduction on my website. And if you go this one and you, here there is a bar below this. Okay, and so this is the introduction to combinatorics, and maybe in the following years, so I will do a class on the whole theory of heaps with relation with physics, algebra, and many other things. And there is also a whole 24-hour classes about orthogonal polynomial. And if I have still in this world, there is this very beautiful also. I put everything under the same roof. Every object which is appear on a tableau, which can be drawn on a square lattice, can be related to quadratic algebra, and so there is a whole theory. So people in IIT last year, they get all this, all this in the mixture of all this very fast. So now I have a lot of time to go slowly and to do this. So this will be the introduction to the 3 other classes, and that's all. Okay. Thank you very much.